This week's focus in your geography lessons for revision is all to do with tectonic hazards. Now, you haven't covered tectonic hazards since year 9, so this could be on a range of scales for you. Whether that be you need to have a lot of revision dedicated towards this topic because you've got a lot of gaps to fill, or you feel pretty confident on this and don't feel like you need to spend that much time on it. So whichever boat you feel like you are in, there are two options for you. First option, if you're feeling confident, is an A3 sheet, which this revision sheet is available to you so that you can fill in notes and complete that. The other option, if you are feeling like you need a little bit more support or you need to go into a little bit more detail, is there is a booklet available for you that I've created. So that just goes into more detail. It's the same content, just a little bit more detail. So that is up to you to decide how much information you need to cover, how much detail you need to go into. So first of all, what I would like you to do is to match the labels with the sections of the earth they go with. So feel free to pause this video now on your device, match them up, have a think about if you can remember any specific characteristics of each layer of the earth as well. So now that you've paused that, you should have had a go at that, and we'll go through which layer matches up with which label. So the first one is the crust, then you have got the mantle, then you've got the outer core, and then the inner core. So on this slide you are faced with 4 different information cards, and your job is to read through the information given to you on each of these cards about temperature, thickness, density and material, and you will need to match those up with the different layers of the earth. So if I were you, I would pause the video now on your device, give yourself a minute or two just to have a read through and see which layer you think it is, and then you can come back after that and see whether you were right. So I'm going to give you a couple of seconds now to pause the video, and then I'll start going through the answers. Okay, so let's have a look at the first one. So temperature is an average of 22 degrees Celsius. If I imagine this, it's a bit like a warm summer's day in the UK. Thickness, this is the thinnest layer of the earth. Density, this part is solid. And material is mainly granite and basalt. But what I will say here is there are other rock types. Now, this last bullet point on this bit, continental and oceanic crust, there is a dead giveaway in this bit. So if you said crust for that one, well done. Next one, so temperatures between 5,000 and 6,000 degrees Celsius. Thickness is 2,500 kilometres thick, and the density is solid. Material is iron and nickel. So when you hear this layer described, you often hear it as said as it is a solid ball of iron and nickel. So there your giveaway is that it's a ball, so inner core. That 2,500 kilometres thick, please note, is the diameter across the ball. So if we went from the middle point, it would be 1,250 kilometres the radius. I hope that makes sense. Next one. Temperature 4,000 to 6,000 degrees Celsius. Thickness is 5,150 kilometres deep. The density is liquid of this one, and the materials it is comprised of is iron, nickel, sulfur and oxygen. So if you said outer core for that one, you were dead on. Temperature of this last one, 1,400 to 3,000 degrees Celsius. The thickness here, this is the thickest layer, so it comprises 80% of the Earth's structure. And what I will say is this is where your conveyor belt is going on, which is why you need molten rock. So you need the rock to be able to move, and this is where we get our convection currents here. The material is iron, oxygen, silicon, magnesium and aluminium. So here, obviously the last one, the only one that's left, that is the mantle. Next task. We need to be able to decipher between continental and oceanic plates. So on the screen there you have 12 different characteristics or facts. What you need to do is go through those and on a tree map or categorising those in some way on different boxes on your sheet. Can you please read through each of those and decide whether that is telling you about a continental plate or an oceanic plate. So please pause the video now, give yourself some time to do that, and I'll wait a couple of seconds before I start speaking again. So first up, we have got thicker, 30 to 50 kilometres thick. That is a continental plate. Remember, this is where we might have some of the mountain ranges, so they are going to be likely to be the thickest parts of the plate. So therefore, the thinnest parts of the plate, below sea level, are the oceanic plates. The plate that is more dense is the oceanic plate. It is heavier, even though that might go against your natural instinct to think a thicker plate will be heavier. It's not. The oceanic plate is denser because of the rock that it is comprised of. So therefore, the less dense, lighter plate is the continental plates. Up to 200 million years old is the oceanic plate. So remember, oceanic crust is constantly being subducted and destroyed. The next one is up to 4 billion years old, that is the continental plate. The plate that is mainly made up of basalt is the oceanic plate, that is that dense, heavy rock. And the continental plates are mainly granite. I went to say granitic. Granite. The continental plate does not sink. Because it is lighter, it is thrust upwards into those fold mountain ranges. And the oceanic plate sinks. The oceanic plate can also, because it sinks, be destroyed. So imagine when that oceanic plate is sinking into the mantle, the high temperatures start to melt it, and then that melted rock is then pushed up to the surface as a volcano. It erupts onto the surface. So remember, as the oceanic plate sinks, the high temperatures melt it, if you would. So therefore, the continental plate cannot be destroyed, although technically it can be eroded. Your next job, we need to know what a convection current is and how it works. So what you have here is a fill in the blanks exercise. If you are wanting to give yourself an extra bit of challenge, cover up that blue box with your hand and see if you can answer those missing gaps. However, if you feel like you need a little bit of help, have a look at the blue box because all of the words are there for you. One word is repeated twice in here, I believe, from what I can remember. So, pause this video now and then I'll go through the answers in a couple of seconds. Right, so, first box, rock is heated in the lower mantle by the core. So remember, the core is the most dense part and it is the hottest part of the earth. So that heat, the radioactive heat, is giving off heat and that is then heating the mantle. So the rock is heated in the lower mantle by the core. And then because, remember, the mantle is molten rock, that can then start to rise. When it reaches the asthenosphere, it cools and is forced sideways by the lithosphere because it is solid. Remember, if those two keywords are upsetting you or you do not know what they mean, have a look back at your keyword sheet that is in the booklet. Next one. It continues to cool and becomes more dense, so starts to sink back towards the core. And then that process continues to repeat. Now, I'm just going to see if this laser pointer works and show you that where these arrows are moving upwards and they will start to push apart like that, those two plates are going to be moving away from each other. So that plate boundary there is going to be a divergent plate boundary. or constructive, whichever phrase that you use. Here, on this side, on the right and on the left, where those convection currents are near the lithosphere and are then starting to sink back down towards the core, they are where subductive plate margins happen. So remember, they are destructive plate margins, but subductive, or collision as well. That's where you can get your fold mountains. You will find this table in your booklet if you are using that. But I do find this one quite useful just to have a little think about the comparison between the different plate types. So if you are feeling confident, have a go at this to start off with, and then you can obviously correct your answers if any of those are wrong. So on the left here, you have the two different types of destructive plate margin, constructive and conservative. What I want you to think about is what direction those plates are moving in. Are they moving towards each other, away from each other, or are they moving alongside each other? Next one, do you get earthquakes at this plate margin? Do you get volcanoes at this plate margin? Can you name any specific features that you might find here? And can you name an example of somewhere in the world that this is found? So we're going to go through these over the next few slides, so your answers will be there. But just see if you can challenge yourself to have a go before you flick to the next one. How much can you remember? Right, so the first one is where two plates move towards each other. They are both continental plates. So this is your destructive but collision plate boundary. Both of the plates are of similar density, so they weigh pretty much the same amount. They're of similar rock types, rock weight. Therefore, because they are the same weight, neither of those sinks, or if you want in a slightly spicier word, subducts. So both of those plates are thrust upwards, and this then creates fold mountains. As they move past each other, friction builds until pressure is released in the form of an earthquake, and no volcanoes are found at this margin. None of the crust is being melted, so therefore we haven't got any production of magma, which can then erupt on the surface as lava. So you don't get volcanoes here, just earthquakes. And an example of this is a fold mountain range that you'll all have heard of, the Himalayas, which is found, well, in a multitude of countries, but I've said Nepal on here. The next one we've got is also a destructive plate boundary, but this is a subduction one. So two plates move towards each other, one is continental and one is oceanic. Now this is a key point here, that the plates are different types. And that's important because the oceanic plate is denser, so it's heavier, so then it subducts, it sinks below the continental plate. And that then creates an ocean trench where those two plates are meeting and the activity is going on. You get a deep ocean trench. As they move past each other, again friction builds until pressure is released in the form of an earthquake. On this plate boundary, where that pressure is released, sometimes one plate rebounds very quickly and a tsunami can be formed, which you can see on this diagram here, where I've attempted to draw a bit of a shocking looking wave. So you do get earthquakes here, and volcanoes are also found at this margin because as this plate starts to sink, it sinks into the mantle and those high temperatures melt it and it turns into molten rock or magma. And then what that magma does is it forces its way through cracks in the rock up to the surface and erupts on the surface as lava, as a volcano. And an example of this is the Andes in Peru. This is a fold mountain range with a deep ocean trench close by. The next one, we have got a constructive plate. That is where two plates are moving away from each other, and both of them tend to be oceanic plates. As the plates move apart, magma then rises to fill that gap, and that forms a mid-ocean ridge. As they move apart, friction builds again until pressure is released in the form of an earthquake. So I hope you're starting to see a trend here. Where plates are moving, friction always builds, pressure always builds, and an earthquake always happens, each plate boundary. Volcanoes are found at this margin because, I don't know whether you've noticed, but we don't tend to have any gaping holes anywhere on the planet. So as those two plates are moving apart and a gap is starting to form, magma then rises to fill that gap and erupts onto the surface as lava. So this is how new land is formed. An example of a constructive margin is the Mid-Atlantic Ridge, and you can see on this photograph here that this is where two plates are moving apart on the Mid-Atlantic Ridge in the middle of Iceland, and you can go and snorkel in between the two tectonic plates. The next one is the conservative plate margin. So two plates move alongside each other. Now this one is important because they can either be in opposite directions, or they're moving past each other in opposite directions, or it can also be travelling in the same direction but at different speeds. So as they move past each other, shock horror, friction builds until pressure is released in the form of an earthquake. No volcanoes are found at this margin because all they are doing is rubbing alongside each other like sandpaper. No crust is being melted, so therefore there is no production of magma, no production of lava, so no eruptions, no volcanoes. And you might be wondering why there is a picture of the rock on this slide. An example of a conservative margin is the San Andreas Fault in California. So I always remember this as the San Andreas film with the rock. Right, so your next one, you needed to do a case study of an earthquake happening in an LIC, a lower income country. So this happened in 2015, and on the board there, on the slide, all that I would like you to do is to look through those 16 cards and decide whether it is a primary effect, a secondary effect, an immediate response, or a long-term response. Remember, a primary effect occurs as a direct response of a trigger, so of a hazard. The secondary effects are things that happen as a result of those primary effects, or they happen later on. An immediate response is something that happens at the point of that disaster happening, and a long-term response is something that happens in the weeks, months, years after that disaster has happened. So again, pause it, and then I'm going to flick through the slide really quickly so that you can mark your own answer. I don't need to talk through each of these. What I will say is, for this one, I just want to explain how it is a secondary effect. So your primary effect was that the clean water supply was blocked. Your secondary effect is that people couldn't drink clean water, so became ill as a result of that primary effect. So they became ill with typhoid because the water supply was blocked because of the earthquake. The other one is that an avalanche was triggered, that is the primary effect, and then as a result of that, 18 people died. Sometimes it can be a little bit tricky to distinguish between primary and secondary. Your next one for New Zealand, I've used the same colour coordination. The blue is the primary effects, green secondary effects. So pause this video and add to your booklet some primary and secondary effects. And on this slide we have got, for New Zealand, the Kaikoura earthquake in 2016. We have got the immediate responses in that yellow-orange colour and the long-term responses in the pink colour. Once you have got these two case studies side by side, which I will always create a resource for you to have them side by side, so you've got that in your booklet, what I would like you to do is start comparing, start drawing links between them. So because New Zealand is your HIC case study, a high income country, and you have got Nepal, which is your low income case study, what I would like you to do is to draw similarities and differences between them. So look at the primary effects, which had the most severe primary effects. Look at the secondary effects, which had the most severe ones of those. Out of the two, a HIC and a LIC, who would you expect to have the better responses? And then you can start to think of who's been successful, who hasn't been successful. How could this disaster have been managed better? Which then leads us on to the question of, why do people live in areas prone to tectonic hazards? Now, these reasons I have separated into social, economic and environmental, and I will talk through those, but please note that with some of these there is a little bit of a wishy-washy grey area. So the first social one is that people's families have lived in the area for generations and they don't want to leave their family. So even though there is that risk there of potentially having an earthquake or a volcanic eruption or even a tsunami, people's families live there and people don't want to live in a lonely place. They don't want to move away from their families, typically. And also, people might not have the money or resources to leave the area. So even if they did decide that they wanted to leave, they might not have the capacity to do so. And what you will notice is that in tectonically active areas, you do tend to have quite a lot of poor areas or impoverished people, because it is so dangerous, and people who have money would rather live somewhere safer. So those people that are in those areas tend not to actually be physically able to leave because they don't have access to the money or the resources. The next one is economic. So the fertile soil around volcanoes is great for farming. I'm going to come back to that word fertile when we talk about the environmental reasons, but basically all I want you to understand is that there is a higher crop yield. So people who live there can grow more crops and therefore get more money for their crops. Because the fertile soil is there, they can also grow better crops, so healthier, more nutritious crops that just turn out generally better because of that soil. So they can also fetch more money for that product as well. Another economic reason is that tourists are attracted to the volcano. So if there is a number of people arriving and they want to give you money to be guided around the volcano, or they want to pay money for souvenirs or tours or anything like that, that increases money in the local economy, so people are going to stay there. And then the final one is that minerals are contained in lava, so things like diamonds, silver, gold, these can all be mined to make a lot of money from those. Now we move on to the environmental. So volcanic eruptions fertilise soil. So that word fertilise and fertile, you might have heard about fertilise before, but basically that the volcano, as it erupts, the ash and the lava contain minerals, lots of minerals which plants really like, and they treat it like rocket fuel. So it can mean that the surrounding area is a lot more luscious, but also that they can grow crops a lot better, a lot bigger, and contain more nutrients. So again, that links back to the economic sector where they're getting more money for it. Geothermal energy. So because the ground around the volcanoes can be a lot hotter further down, that can be used to generate electricity. And as I've already touched upon, a wide variety of crops can be grown due to the fertile soil. So that can be cocoa, pineapples, olives, tomatoes, citrus fruits. Now that obviously depends how close you are to the equator, because you can't exactly grow tropical foods in Iceland, but the fertile soils help a lot. And a final one is that ocean trenches on those subductive plate margins provide deep ports for trade. So a lot of people will live near the ocean in these tectonically active areas, because there is that ability to use the port to trade and to get boats and ships and containers in. So the final bit that we need to think about is the 3 Ps. So have a little think about whether you can remember what the 3 Ps are. First one is predict, then it is prepare, and then it is protect. So what we're going to do now is we're going to spend some time trying to understand what each of these 3 things are and mean, because at first glance you could think they are quite similar. And then you are going to gather some information for your booklet or your A3 sheet of paper. So the first thing you're going to do is match up the definition with each of those words. Please pause the video now. I'll wait a couple of seconds and I'll go through the answers. So the first one, trying to forecast when and where an earthquake or eruption will happen so that an evacuation can take place. That is prediction. The next one, oh wait, I'll go back, sorry, going too fast. So if you can forecast when something is going to happen, you are predicting when it is going to happen. And that will then allow you to help people as a result. So people try to predict, although what we know is that earthquakes can be very, very difficult to predict. The next one, building to an appropriate standard and using designs to withstand tremors and movement. So that can be things like using building codes to help create buildings that will withstand the tremors. That is protection. You are protecting people. And the third one is obviously preparation, because you are making sure the emergency services and public are prepared. They know the procedures to follow in the event of an earthquake or eruption. So what we're going to do now is we're going to go into a little bit more detail about the examples, the strategies that each of these 3 Ps cover. So the first one that we're going to look at is predict. So what I would like you to do is just looking at those pictures, see if you can guess what those involve in the prediction process. So pause the video and then I'll go over it. So the first one, it has been noted that sometimes, and the keyword is sometimes, it is not a foolproof method. Sometimes radon gas is emitted prior to an earthquake. So if there is an increased amount of radon gas being emitted from the Earth's crust, sometimes it has been correlated with an earthquake that has then happened. So that can help people to predict. Another one is that laser beams monitor changes in the size of volcanoes and jolts in the Earth's crust. So if you think in the desert in California, that is a very large area that would be very costly to sit and monitor. So what scientists have done is they have used laser beams along the San Andreas fault or along bits of the fault, and then once those laser beams are broke, it's a bit like a spy movie, once those laser beams are broke, they know that the Earth's crust has moved, and then that can help them to predict if a bigger earthquake is about to happen. Satellites trace movements in the Earth's crust, so it can help them to understand how far the tectonic plates are moving apart, but it can also be used for really useful things like monitoring the size and shape of volcanoes. So if you imagine as a volcano is getting ready to erupt, that magma is starting to rise, and therefore the volcanoes can sometimes get a little bit of a bulge on the side. So if a satellite is monitoring the size and shape of that volcano, any changes, they can start to think, oh, I wonder if that volcano is about to blow because it is changing in shape. So that could be the magma that is moving around in there. And then finally, hopefully you did get this one, it is seismometers, and they track movements in the Earth's crust. So if that Earth starts grumbling a little bit, as the Earth is getting restless, they can get the warning out that an earthquake could potentially be about to happen. Although that isn't a foolproof method, again, because sometimes they do just happen unpredictably. The next one is prepare. So again, pause this video, give yourself some time to have a think about what is going on in each of these pictures. So the first one is that people keep earthquake survival kits in their homes. A lot of people in tectonically active areas keep these kits or suitcases or grab bags just ready to go in an emergency, and it's got things in like water, first aid kits, radios, lamps, torches, like cans of food, just in case like something happens and they have to leave, or something happens and they're stuck in their homes, so they've got things available to them. The next one is that Japan holds an earthquake drill day on the 1st of September every single year, and this is a full coordination between the emergency services, schools and businesses, and basically they prepare themselves by practicing what to do in the event of an earthquake drill, just so everybody knows what to do and they can minimise the amount of injuries and life lost in the event that a big earthquake happens. And then finally, posters are displayed to remind citizens of what to do in the event of an emergency. So here on this one, you can see that they've got the drop, cover, hold on message available for people. Protect. So again, pause this and see if you can come up with what it is that I am thinking of. Right, so that big red button was meant to signify or symbolise an automatic shut-off switch, and that can be fitted to gas and electricity supplies so that in the event of an earthquake or a volcanic eruption, there are not fires created, because that is often a massive issue. The next one is that you can build earthquake-proof buildings, so you install rubber shock absorbers, you use flexible steel frames, which helps buildings to sway during an earthquake. And then finally, money invested in emergency services and education programmes. So this is obviously easier for HICs than for LICs because they have more money available to them. But if they invest their money in the emergency services and their education programmes, they are protecting their people because those funds are available. It's also similar if they've got funds put to one side for in the event of a disaster and emergency. So, bit of a whirlwind that, but I hope that's helped you fill in that booklet a little bit, or your A3 sheet of paper. Thank you for listening, and I hope that you found this useful. As always, please offer some suggestions if you would like anything to be done slightly differently, or you would find something beneficial. Okay, thank you.